Lab-grown diamonds are one of the most fascinating scientific and industrial achievements of our time. Stones identical to natural diamonds in chemical composition, brilliance, hardness, and optical performance, yet created entirely inside controlled laboratory environments, where extreme heat, pressure, plasma, and atomic-level precision turn carbon into crystal. Most people have seen a polished diamond sparkle under a jewelry store light, but almost no one has witnessed the full transformation. How raw carbon becomes a flawless gemstone, how plasma reactors grow atomic lattices, how diamond seeds replicate themselves layer by atomic layer, or how master polishers shape a rough man-made crystal into a brilliant round stone worth thousands. And today on the How Factory, we're going deep inside the high-tech world of gemstone engineering to reveal how lab-grown diamonds are created, grown, cut, polished, graded, inspected, and prepared for the jewelry industry. The journey begins far from the elegance of the final product, in warehouses filled with high-tech furnaces, vacuum chambers, microwave generators, and systems capable of replicating the extreme forces found deep inside the Earth's mantle. Forces that naturally take billions of years but are recreated in a matter of weeks using advanced industrial science. Lab-grown diamonds come from two main technologies: high-pressure, high-temperature, known as HPHT, and chemical vapor deposition called CVD. Both methods begin with a tiny, incredibly important component: the diamond seed. A seed is a thin slice of diamond, often less than a millimeter thick, carefully cut from a larger diamond crystal. These seeds serve as the blueprint for new growth. In the same way that a snowflake can grow by accumulating layers of ice, a diamond seed grows when more carbon atoms attach to it under the right conditions. Seed preparation is precise. Technicians clean each seed in ultrasonic baths that remove microscopic dust, oils, and contaminants. If anything remains on the seed, it can disrupt crystal growth, causing inclusions or structural defects. After cleaning, seeds are sorted by size and quality, so the growth process can be controlled as accurately as possible. For HPHT diamonds, the process begins with a massive press. These machines, sometimes weighing more than 50,000 pounds, are capable of producing several million pounds of pressure and temperatures exceeding 1,500 degrees Celsius. To grow a diamond this way, engineers place the tiny seed inside a growth capsule filled with a carbon source, typically graphite, and a mix of metallic catalysts such as iron, nickel, or cobalt. These catalysts help carbon atoms rearrange themselves into a diamond crystal structure instead of graphite. The capsule is then loaded into the press. When the press activates, it uses anvils or belt-shaped structures to compress the capsule with extraordinary force. The temperature rises, the catalysts melt, and carbon dissolves into the molten mixture. As the mixture cools slightly under pressure, carbon atoms begin to crystallize onto the seed, replicating its lattice structure. This process can take days to weeks depending on the size of the diamond being grown. Throughout the growth cycle, sensors measure pressure, temperature, and thermal gradients. Even small inconsistencies can cause the diamond to crack or grow with internal strain. Technicians monitor the system constantly, making adjustments as needed. CVD diamonds grow in a very different environment. Instead of extreme pressure, CVD uses plasma, a glowing cloud of ionized gas, to build diamonds one atom at a time. The process begins with a vacuum chamber. Technicians place the seeds on a heated stage inside the chamber. Then, they introduce hydrogen and methane gas. Microwaves or radio frequency energy ionize the gases, forming plasma. Inside this plasma, methane splits apart, releasing carbon atoms. These carbon atoms slowly fall onto the diamond seed and bond to its surface in perfect cubic layers, expanding the crystal vertically and horizontally. The process functions like molecular stacking, microscopic layers accumulating one after another. The environment is incredibly controlled. Temperature, gas purity, pressure, plasma density, and electrical conditions must all remain within tight tolerances. If any variable drifts, the growing surface can become cloudy or structurally distorted. A CVD diamond typically grows at a rate of 1 millimeter every few days. Large stones may take weeks. During growth, engineers check the crystal with optical sensors, laser scanners, and spectroscopy tools that detect impurities in structural alignment. If nitrogen or boron atoms enter the chamber, the diamond may grow with unwanted color. Many high-end producers therefore use gas purification systems that strip contaminants down to parts per billion. When the diamond reaches the desired size, the plasma is switched off, the chamber cools, and the newly grown rough diamond is removed. Once the rough diamond exits the press or chamber, the next step is annealing, a controlled heating process that relieves internal stress created during growth. Annealing stabilizes the crystal lattice, improves clarity, and corrects any color inconsistencies caused by metallic inclusions in HPHT growth or structural strain in CVD growth. Diamonds are loaded into high-temperature furnaces and heated to several hundred degrees or sometimes over 1,000 degrees Celsius, depending on the type of correction needed. The diamonds are then cooled slowly, allowing internal tension to relax. This step is critically important because diamonds that retain internal stress can crack when cut or polished. After annealing, the diamonds move to the planning stage. Rough diamonds, even lab-grown ones, rarely have perfect shapes ideal for jewelry. They often appear jagged, cloudy, or uneven. Diamond planners use lasers, 3D scanners, and specialized imaging systems to map every internal feature. They identify inclusions, cracks, growth lines, and the best way to cut the rough stone for maximum clarity and carat yield. This planning process determines whether a rough diamond becomes 2 small stones, 1 large stone, or a specific shape like round, brilliant, princess, oval, or cushion. Planning is both an art and a science. A great planner might recover 40% more usable material from the same rough compared to an inexperienced cutter. Once the planning blueprint is finalized, diamond cutting begins. Cutting a diamond is unlike cutting any other gem. Diamonds are the hardest known natural material, 10 on the Mohs hardness scale. So only another diamond can cut or grind a diamond. The first major operation is cleaving or sawing. Lasers or high-speed diamond-tipped saws slice the rough stone into manageable sections. Sawing is delicate. If the cuts follow the wrong grain direction, the diamond can shatter. After sawing, the next step is bruting, shaping the diamond into a round form. In traditional diamond workshops, this was done by rubbing 2 diamonds against each other, but today, most factories use high-precision computerized lathes and diamond-coated grinding wheels. Bruting shapes the girdle, the outer edge of the diamond, giving it the initial circular outline needed for a round brilliant, or the angular outline for fancy shapes. When bruting is complete, the diamond moves to fasting. Fasting is the process of cutting flat surfaces, called facets, onto the diamond to enhance brilliance and fire. A standard round brilliant diamond has 57 or 58 facets depending on whether the culet is faceted. Each facet must be placed at exactly the right angle and position. Even a half-degree error can affect sparkle. Faceting machines use diamond polishing discs called scapes. The cutter presses the diamond against the spinning scape at precise angles, guided by computerized arms or manual controls depending on the manufacturer's style. The first set of facets, called the pavilion facets, determine how light enters and reflects within the diamond. Next, cutters create the crown facets, which control how light exits the diamond, producing the bright flashes known as brilliance. The table facet, the large flat top surface, is cut last or near the end because it determines the final symmetry. Throughout the process, cutters pause frequently to inspect facet alignment under microscopes and 3D measurement systems. Lab-grown diamonds typically show fewer natural growth deviations than mined diamonds, making them easier to cut with predictable optical results. But precision is still critical. A single mistake can ruin an expensive stone. Once faceting is complete, polishing begins. Polishing refines each facet to a mirror-like surface. During polishing, technicians adjust the diamond's angle, pressure, and positioning with exquisite control. Even the slightest vibration can leave faint polishing marks known as burns, or microscopic lines that reduce brilliance. State-of-the-art polishing labs use vibration-isolated tables and laser-aligned arms to achieve perfect finishes. The goal is total symmetry. Each facet should mirror its opposite side with ideal proportions. Achieving this requires skill, experience, and patience, even with modern machinery. After polishing, diamonds undergo a final cleaning process in acid baths or ultrasonic tanks to remove polishing residue, graphite dust, and metal particles from the cutting equipment. At this point, the diamond is fully cut and polished, but not yet ready for the market. Every diamond must undergo grading. Grading evaluates the diamond according to the 4 C's: cut, color, clarity, and carat weight. Laboratory-grown diamonds are sent to gemological labs such as IGI or GIA for certification. Graders inspect the stone under 10 times magnification to identify inclusions, surface blemishes, growth patterns, and any metallic remnants from the growth process. Lab-grown diamonds often show unique internal features. CVD stones may reveal striations from layer-by-layer growth, while HPHT stones can show metallic flux inclusions. These are natural characteristics of the creation process and do not necessarily affect appearance. The diamond's color and clarity are rated, and its cut grade is determined by analyzing proportions, symmetry, and light performance. The diamond is then weighed on a microbalance capable of measuring to the 10,000th of a carat. Finally, lasers engrave a microscopic certification number on the girdle. This inscription is invisible to the naked eye but allows jewelers and consumers to verify the stone's authenticity and origin. After grading, diamonds proceed to sorting. Manufacturers categorize stones by size, shape, clarity, color, and cut grade. Large batches are then sold to jewelry designers or wholesalers who mount them into rings, necklaces, bracelets, or earrings. Some diamonds go to industrial sectors, and because lab-grown diamonds also play crucial roles in cutting tools, heat conductors, electronics, and quantum computing. But most high-quality stones head to the jewelry industry. Before mounting, diamonds undergo one final inspection. Jewelers examine the stone under microscopes to ensure there are no chips, scratches, or polishing marks. If needed, the diamond is given a light repolish to perfect its face before setting it into a metal prong or bezel. Advanced jewelers use laser welders, CNC milling for settings, and CAD-designed mountings crafted with exact dimensions for each stone. Once mounted, the diamond is cleaned, inspected again, and prepared for sale. But behind the glamour of the final jewelry piece lies a vast industrial chain. Reactor maintenance, vacuum chamber cleaning, gas purification, metal catalyst recycling, optical monitoring systems, and quality control labs ensuring every stone adheres to strict gemological standards. CVD chambers must be periodically cleaned to remove carbon buildup. HPHT presses require maintenance on their anvils, cooling systems, and hydraulic drives. Gas handling systems must remain ultra-pure to prevent contamination. Technicians log every growth cycle, documenting temperature curves, pressure logs, plasma stability, and carbon consumption rates. Even the diamond seeds themselves undergo recycling. Leftover seed material is cut again into thin slices to begin another growth cycle. What makes lab-grown diamonds remarkable is not just their beauty, but the science behind them. CVD diamond reactors operate like miniature suns, with glowing plasma fields where carbon atoms float freely before crystallizing into gems. HPHT presses mimic geological conditions with engineering precision. In both cases, human innovation compresses geological time. The natural processes that take millions or billions of years underground are replicated in weeks above ground using physics, chemistry, and advanced engineering. And once you witness the manufacturing behind these stones, the extreme heat, the molecular growth, the mechanized precision of cutting and polishing, the microscopes, the lasers, the diamond-on-diamond grinding wheels, you realize why lab-grown diamonds are more than just jewelry. They're engineering marvels. They represent the intersection of nature's blueprint and human ingenuity. Every polished lab-grown diamond carries inside it a story A story of carbon atoms assembled with scientific mastery. A story of modern manufacturing pushing boundaries. A story of how technology can recreate one of Earth's rarest materials. And that is exactly how lab-grown diamonds are created, grown, cut, polished, graded, inspected, and prepared for the world of jewelry. A breathtaking mix of atomic science, engineering, industrial machinery, craftsmanship, and precision. Thanks for watching The How Factory, where we reveal how the world really works. Don't forget to like, subscribe, and stay tuned for more deep dives into the incredible systems behind everyday technology.